Reference counting is one of the earliest and most straightforward garbage collection strategies. The idea is beautifully simple. Every object in memory has a counter attached to it. This counter keeps track of one thing: how many references are currently pointing to this object. That's it. Reference counting follows 4 simple rules. Rule 1, when an object is created, its reference count starts at 1. Someone just created it, so there's at least 1 reference to it. Rule 2, whenever a new reference is made to the object, the count goes up by 1. We increment the counter. Rule 3, whenever a reference to the object is destroyed, the count goes down by 1. We decrement the counter. Rule 4, if the reference count reaches 0, the object is immediately deallocated. No references means nothing in the program can access it anymore. It's safe to free that memory right away. Let's walk through an example to see how this works. We create a new person object for Alice. The object is allocated on the heap. Look at the counter. It starts at 1. We have 1 reference to this object, the variable person_a. Everything is tracked automatically by the runtime. Now let's say we create another reference to the same object. We assign person_b to point to person_a. Both variables now reference the same Alice object. Watch what happens to the counter. It increments from 1 to 2. The object now has 2 references pointing to it. The reference counting system tracks this change automatically. As long as the count is above 0, the object stays alive. Now let's remove one of the references. We set person_a to null. This destroys 1 reference to the Alice object. Watch the counter decrement from 2 to 1. The object still has 1 reference, so it stays in memory. Person_b can still access it. Nothing gets freed yet. Now we remove the final reference. We set person_b to null. This destroys the last reference to the Alice object. Watch the counter drop to 0. The moment it hits 0, something important happens. The object is immediately deallocated. The memory is freed and returned to the heap right away. There's no waiting, no scanning, no pausing. As soon as the count reaches 0, the cleanup happens. This immediate cleanup is the key advantage of reference counting. Memory is freed as soon as it's no longer needed. There's no delay between an object becoming garbage and the memory being reclaimed. This predictable behavior makes reference counting attractive for certain use cases. Reference counting is used in several real-world systems. Python's default implementation, CPython, uses reference counting as its primary garbage collection mechanism. C++ provides smart pointers that use reference counting to manage memory automatically. Swift uses something called automatic reference counting, or ARC, to manage memory without a traditional garbage collector. These are production systems running in millions of applications. Reference counting seems elegant and efficient, but there's a critical flaw. What if the reference count never reaches 0? What if an object is garbage, but the counter stays above 0? This can actually happen. In our next lesson, we'll discuss the problem with reference counting. Subscribe, like, and share.